Welcome to this week where we are going to be working in C++ again and making a very detailed program that's going to do a lot of fun stuff in binary search trees. And I chose to go with an AVL tree to make the balance self-balancing. And in our program, we're going to be adding, removing, finding, and displaying maximum values. We're going to be handling the edge cases, such like removing an empty tree and attempting to insert duplicate values. We're going to include an in-order traversal method to display the tree's contents. And we're going to, for testing purposes, demonstrate the functionality with different test cases. And my favorite, we're going to use prime numbers as the node values in each of our test cases. And for our performance analysis, we will be working with various given large node values and measuring the time it takes to insert into those nodes. Each node of a value being 100, 1,000, 10,000, and 100,000. We'll be using our prime numbers for the performance testing and outputting the performance data to a CSV file for further analysis. That analysis, in essence, we're going to be looking to see what kind of data plotting with the different values for the data sizes. And ideally, we'd like to see something linear, but I have a feeling with the complexity of this that it most likely will not be linear, but we shall see. In any case, we will also be analyzing 3 questions on how the performance changes as the number of nodes changes, why the difference in performance and what's the cause, and in what case would each structure be preferable. So with the program, we're going to print messages which will confirm the addition of each prime number, and after an insertion, it will display the tree's contents using in-order traversal, showing the numbers in ascending order. If there is a duplicate, it will output a message indicating that duplicate data is not permitted. If we try to remove a node, we will get a message printed specifying which node has been removed, and after each removal, we will display the updated tree contents back in the in-order traversal method. If we need to find a node, we will output whether the specified prime number was found within the tree. And finding the maximum value, simply displaying the maximum prime number currently left in the tree. And for the performance analysis, our console output will set each prime numbers into 100, 1,000, 10,000, or 100,000 data sets. And the program will print the number of primes being inserted and the time taken in milliseconds how it inserted them into the AVL tree. Within our CSV file, we're going to extract the performance data in a tabular format and be able to plot that data and see again what kind of data we have. what the line looks like. Each row will correspond to a text case and recording the number of primes and the time taken to insert them. So without further ado, let's go ahead and run the program. And it quickly calculates that our program has started. The current working directory depends on your environment. Obviously, if you have a slow computer, it's going to calculate things more slowly. We're dealing with large data sets going up to 100,000, and depending on the system, it could put a little bit of burden on it. And we are going to add our prime numbers to our binary search tree. Our binary search tree, after adding our prime numbers, I just picked some basic ones because I didn't want to get real complex. And we put them in order traversal, so you can see they are all nice and ordered. And when we insert a duplicate prime number, such as 13, we are told that we cannot duplicate 13 because it's already in our tree. And when we remove a leaf node, I chose 29, we see that 29 is no longer in our tree. And if we remove a node with only one child, which in this tree was 19, we see 19 is now vacant in our list. And if we removed a node with two children, which in this case was node 13, or the node containing 13, I should say, now 13 is blank between 11 and 17. And when we randomly find a prime number, we chose 17, it located the prime number 17. And to calculate the maximum prime number in our binary search tree, we looked at all the values, and 23 was the highest value I entered, and it calculated that 23 was the highest in our tree. We get to our performance analysis, and we start seeing a small trend, but I've got a very, very, very fast computer. I won't lie. It's quick, and it's hard to tell with a 0 millisecond for our 100 and a 0 millisecond for our 1000, and then only going to 3 milliseconds for 10,000. We're not getting very, very accurate data. We need to probably break this down into a smaller number to really see the effect. So I may need to take another look at that and break that down maybe into microseconds and see how that data comes out. But nonetheless, we see that it does start to increase very, very gradually, but it is non-linear. From 0, 0 to 3 to 47, that is quite a leap. And I'm going to go out on a limb and say that if we threw it up to 1 million, we'd probably be looking somewhere into probably 200 milliseconds, I'm guessing, if the math was correct. Maybe 100 milliseconds, give or take, maybe the high. But what I'm saying is we're not seeing a linear progression here. What we're seeing is a logarithmic trend, and that actually matches up to what we're doing because we are using an O log n algorithm And from the big O chart that we're all so familiar with, we know that an O log n algorithm is going to have a higher curve to it and thus not be linear. So we can see how, like I was pretty much guesstimating, we can see already that this trend is going to start to rapidly increase when our n value starts to increase. So we're only at 100,000. Let's just say we did 1 trillion. We could be working with computer times that would affect our program very heavily. And essentially that's what we're trying to mitigate or understand, is how these values and these algorithms work with systems, and understand that time is of the essence and system time is of the essence. We'll go ahead and clear this, make sure it is stopped, and with that I think we are pretty much good.